All right. Okay, I think I'm going to get started. So I'm pretty fine with people just jumping in if you have a question or something to say. Sorry, 1 second. I've got to trust my iPad here. I'll open the chat too so that I can see if people are more comfortable. People are more comfortable writing something in the chat, they can. Okay, there we go. All right. Chat though. Okay. Okay, I think I have everything. 1 second, guys. Almost there. All right, good to go. So today, we're going to talk a little bit about, we're going to move on to chapter 7 and talk a little bit about the material there. And we get a little more into some of the, I don't know, some of the finer notions in graph theory that are very common. And again, there's a lot of nice applications of these. You can see in all sorts of.
What?
You've been missing me.
Oh, sorry.
I'm sorry.
That's all right, Jenna. I'll mute
Nothing.
you. Was it a question? If you have a question, yeah, sorry, unmute yourself. I didn't want to mute you if you have a question. All right. All right. So we're going to talk about networks. And okay, so let me start. This is a picture of a network. Okay, it's really a graph, I guess, according to the book's definition, but maybe the center part is a network. It's an Instagram network that someone has of their friends and their friends' connections. So I don't know, I thought it'd be a nice kind of thing to see that these are actually used by computer programmers to, I don't know, understand people's social networks. So what is a network for us? So a network for us is going to equal, it's going to be a graph that's connected. Okay, that's it, just a connected graph. And there are some notational differences if you're talking about networks. I don't know why, but this is certainly in computer science and a lot of applications. When you're talking about network, oftentimes you'll call vertices nodes and edges will be called links. I'll probably stick with edges and vertices. But this is just something you'll see if you look in other other areas. Now, one of the things you can do is if you have a graph, is you can talk about it, you can create a sense of distance, sort of a definition of distance between two vertices on the graph. And so that's really helpful if you want to sort of, I mean, we've already talked about sort of minimizing length or of circuits or Hamilton paths, but let's talk about just the sort of graph theoretic notion of distance or degree of separation. So there's a notion of, this is the same notion, degree of separation or distance. And this is going to be between two nodes or vertices. This is going to be the length of the shortest path between two vertices. And those are generally given, so between two given vertices. So I won't use that graph, but we can look at, I'll just draw another graph, say something like this. To something like this. Okay. Actually, let me get rid of this one. All right, so if I look at A, C, D, let me label these vertices, A through F. Let me ask you guys what is the degree of separation between A and, let's say, D? It's there. It's been a while since I've Zoom taught, if you want to call it that. A and D? 2, good. Right, so if we look, we've got a path of length 2, and that gives us our distance. So of course there are other paths. This is the thing I want to mention, right? We can look at a path like that, that's length 3, but if you're finding the degree of separation, you're looking for the sort of smallest path, the shortest path. That will give you your distance. So another concept with this is the notion of diameter. And so the diameter of a graph is going to be the the maximal distance or maximal degree of separation. So the largest degree that you can find of separation between any two vertices. Sorry, I'm spelling things here. So let me ask what the diameter of this graph is. Think here. Five. Joseph says 5. I think I understand what you're saying, Joseph. So, and I want to clear it up a little bit. So, there is a path that's of length 5, and that's probably the longest path you can find in this graph. So, I think that's where you're coming from, which is a thing to know about this path. However, the diameter is the maximal degree of separation. So, when I look at this path, say, while this path has length 5, the degree of separation between A and F is not 5. it's 3 because I can find the shorter path. So what you're looking for is that largest degree of separation, not necessarily the longest path that you can find. So in that case, does anyone have a thought? What it could be? You guys there? 3, great. Yeah, so this is 3 in this case. All right, that's right. So there's this notion of diameter, there's this notion of degree of separation. I mean, I know there's this like Kevin Bacon game that they play. Well, I don't know, they've been playing it forever. I tried to see if there's any kind of like similar game now. I don't know who Kevin Bacon would be now. Actually, there was a Reddit stream about this. Someone suggested John C. Reilly, apparently. I don't know. Any suggestions? What's the better Kevin Bacon? Like everyone's like supposed to be within what, 3 or something of Kevin Bacon. So if you draw, yeah. Uh-oh. Request a live transcription be enabled for the meeting. Sure, I don't know what that means. Okay. Oh, okay, yeah, I see. Now I'm scared of myself. What is that? Ah, okay. All right, so I'll ignore that as much as I can. So yeah, what do people think? No one has any suggestions with like Kevin Bacon or like a current actor that could be like approximately close to every other actor? Anyway, Kevin Bacon's supposed to be like, what? I don't know what the degree of separation for Kevin Bacon is, but it's supposed to be very small. It's not really a math question, but okay. All right. So these are some notions that we want to have, but now there's sort of a major notion that we want to get to and talk a lot about today. And that's the notion of a tree. Which, yeah, I know, I mean, people know what trees are, but we're going to talk about mathematical trees. All right, so a tree has a particular kind of graph for a mathematician or for someone who's applying math or thinking about graphs. So a tree is a connected graph without any circuits. Does it make sense? Everyone's nodding their head. That's good. Okay. So here's a tree. Here's a tree. Okay. As you can see, okay, I mean, sort of, I drew it in a way that it looks like a tree, but kind of. But the point is that there's no circuits. It's connected. That's one part, but there's no circuits. So I'm not going to be able to ever go around and loop back. So that's the notion of a tree. Questions? So if I draw something like this, let's say my graph is this, is that a tree? No. No tree here. This is not a tree, right? Because it's not connected. Connected means that you can get a path between any two vertices. So here we can see on this side, we don't have paths between the sort of part on the right and the part on the left. Also, we could draw another non-example. Say we have something like this. This is also not a tree because we have a circuit. If we look at something like that. So for a tree, sometimes we want to actually distinguish a particular vertex of a tree, which we call a root. So usually if you draw a tree and you distinguish a root, you'll put it at the bottom. Sometimes you'll put it in the top. Oh, no connection. Can you hear me, Joseph?
I was saying like no connection as in like why that's not a tree.
Ah, okay, good. Yeah, I understand. That's right. Right. This one here. Great. So what I was going to say was sometimes people, there was a mathematician once met who was from Australia, and he said that they drew their trees the other way. Like they would draw their trees that way, because he said this because he was, on the southern hemisphere. I don't know if that's true or not, but I mean, he was kind of a little bit of a ridiculous guy. All right. So trees are very useful things, as we'll see in a moment. They're very, very reasonable things to consider. They occur all over the place in applications. In so many different areas, it's hard to, I mean, any area where you have some kind of graph theory problem, it's very common you'll see trees appearing within that. And so computer science and logistics and finance and all that stuff have a lot of trees. And physics. Anyway. So let's talk a little bit about them. There's some basic properties we want to have available. The first they call a single path property. Which just says, so given a tree, I'll just say given any two vertices in a tree, there's exactly one path between them. In a sense, that makes some things a little easier, right? I mean, if we talked about, just a second ago, we talked about degree of separation, and we had to kind of look over, try to find all the possible paths between two given vertices and sort of find the smallest one. But in a tree, there's only one. So you don't have to go through that exercise in as much detail. You can just find that one path and then count up the edges. And it's not too hard to see kind of why that's true. So let's say I look at this tree here. I'll copy it and bring it down. So let's say I have this tree here, and I'll take the root for one of my vertices, and let me look at another vertex. I'll put it over here. And you can see, of course, there's only one path here between these two vertices, which is drawn in red now. And what I would like you to imagine, though, is what would go wrong if there was another path. So maybe someone can tell me what would be the problem. Why does this single path property, why does it hold? What would happen if I had a different path from between these two vertices? Guys, I'm feeling real lonely over here. I like hearing you guys there. It's been a while since, COVID's been in full screen. I guess there's only like a very small number of people. No, not too bad. Well, it's pretty bad. Okay, like 7, 10. Okay, like less than half the class. That's all right. I mean, it is a snow day. I mean, my kids would hate me if I did this. What was the question? The question was, okay, so I said, so we've got this property here for trees, right? Single path property. Given two vertices, there's a single path between them. That's the property. And I'm asking, what would happen? Why is that property true? What would go wrong if I had another path, a different path between those two vertices? Why would that be a problem? It would not be a path. Well, okay. I mean, let's see. I mean, I'm trying to imagine, don't look at this particular tree. Just say, okay, let's imagine we had some graph here. So there's all kinds of stuff happening here. We don't know what's happening. I'm saying, okay, now I've got these two vertices. I draw a path between them. What would happen if I had some other path in this graph? Let's not say it's not this particular graph. I mean, it's some other tree. It would not be a tree anymore. Libby, I like that response. And I like that response even better. Bailey says it would have a circuit. Right. That's the kind of the thing I wanted to make clear. So if I had another path, let's say I had another path and it starts here, kind of goes over the first edge, but then it kind of goes out somehow, comes around, and then ends on the same edge here. Well, what you see is, okay, there may be some overlap at certain places, but if I get rid of that overlap, I'll get a circuit. Right. I'd have a circuit. And that's violating this definition of a tree says I can't have circuits. That's right. Very good. Small but effective attendance today. Okay, guys. So that's the single path property. And again, it makes, finding a path a lot easier. So if you have a unique one, it's easier to say, okay, this is the path rather than here's a path, and have to compare several different ones. So this is one property. Another property is the all bridges property. And that just says that every edge in a tree is a bridge. And conversely, also, if a connected graph has this property, it is a tree. The same with the last property as well. It's the same kind of notion. And the reason here is sort of the same as previously. If we draw our graph, and we had some edge, so let's say this is kind of like a part of the graph right here that we're looking at. We don't know what's out here. And we look at this particular edge. Okay, well, if this is not a bridge, if this edge is not a bridge, what would go wrong? And again, I'm just imagining this is a part of our tree and I don't know anything about out here and I just see that edge. So what would go wrong if I say this particular edge is not a bridge?
Is it considered a tree then?
Well, so that's the thing, is that it wouldn't be a tree. And the reason is sort of the same reason that Bailey gave for the last property, which is saying, okay, if this edge is not a bridge, what does that mean? That means that I can take away this edge and I'm still connected, which means there's some other path from the top to the bottom. So if it's not a bridge, when I take it away, it's still connected, which means I have some situation like this. So there's some path from here to here. But then when I put it back in again, I look and I see that I have a circuit. So and a tree doesn't have any circuits. So that means that I did something wrong. This must have been a bridge to start with, and I could not have had some kind of situation like this. So in other words, every edge in a tree must be a bridge, otherwise I'll have some circuits. Is it clear? Does that make sense to people? You can just nod your head. I have my ways of seeing it. Oh yeah, right, there's the thumbs up. Gosh, it's been so long. Cool. Good. All right, there's another property, n-1 edges property. So -1 edge tree say with n vertices and n-1 edges. In other words, if you know the vertices in a tree, you know the number of vertices in a tree, you know the number of edges as well. That's so we can take a look. Excuse me. Let's say we have a tree like this. We can count the number of vertices here. There's 6 vertices. And if we count the number of edges, I have 1, 2, 3, 4, 5 edges. So indeed, 5 is 6 minus 1. So that checks out for this particular example. How would you go about making the argument? I'm going to ask you guys, how do you make the argument that this is always true? Does anyone want to brave that question? Why is this always true? Let's say I have a tree. How do I know? And it has n vertices. How do I know there are n-1 edges? One less edges than the number of vertices. Any thoughts? Have a circuit which would make them even. Huh. Ah, are you talking about the vertices being even? So vertices are a little more complicated. The sort of the degrees of these vertices. These pictures I've drawn, I've gotten some trivalent, I mean degree 3 ones, degree 1. There's some degree 2 up here. But the degrees can kind of go all over the place for trees. So the argument of why, let me give you guys, I mean, I don't think it's one of those arguments that takes a little thought. It's actually called an inductive argument. I don't know if you guys have ever heard of an inductive argument before for like math or logic or anything, but it's the idea of, okay, if I know something is true for a certain number, then, and I can kind of go up a number, I can ask the question as whether this formula is true for one larger number. If you can prove that, you can show that, then you can kind of say it's true for all numbers. Because if it's true for one, and two, it's true for two, it's true for two, it's true for three, and so on and so on, then you get it for all numbers. So the thing about this is there's a simple inductive argument which says, okay, if I have two vertices, there's only one tree, and it is this tree here, right? This is the only tree I can have with two vertices. So the number of edges, let me give myself a little more room here, is one here. So it's this formula is true when I have two vertices. Now, if I go to three vertices, I can look and I can think of all the different trees I can have with three vertices. There aren't that many. In fact, they all look the same. They look like this. And okay, I'll just stay right here for three vertices. Again, I have two edges. And now once you get to four vertices, you have some options, right? You can kind of look at this tree. I mean, here I'm not labeling the edges. If I label the vertices, if I label the vertices, I get maybe more options. But kind of I just look at it without labeling, I get two sort of options here. But in both cases, I get three edges. Now, I don't want to do this forever because it's going to be, horrible. So instead, what I can do is I can say kind of a process. I can state a process that where I go from n vertices to n plus 1 vertices. So in other words, I go from 2 to 3, 3 to 4, and so on. One thing I can always do if I have a tree with a larger number of vertices, I can say I built it out of a smaller tree by adding a single edge somewhere. So here I built this guy by adding a single edge there. Or I built this tree by adding a single edge here. Right. So you can say, well, whenever I go up one vertex for trees, the way I can always do this is I can just add a single edge with a single vertex on the end. Those vertices are called leaves. You can think of them as sort of the end of the branches. So, but then what are you doing? You're adding a single vertex and you're adding a single edge, which means the number of edges is going up by 1, just like the number of vertices is going up by 1. So that formula that says that the number of edges is going to increase by 1, just along with the number of vertices, holds, just regardless of how large you are, sort of by induction. Is that sensible? I mean, it's not a formal argument, but hopefully it gives you an idea of why this is true. Okay. And it is an if and only if, which means that if you have a connected graph with n vertices and n minus 1 edges, then it has to be a tree. And that argument's maybe has a little more details, but I'll just, maybe we'll talk about it later in this chapter, I'm not sure. So one thing I want to say is that there are, right, these properties are nice properties, and they're useful to understand. And a lot of the stuff with the graph theory, you can see from many different angles. There's different ways of looking at a graph, and there's different ways of looking at trees. And sometimes it's helpful to look at it or define a tree using one of these three properties instead of the original definition. And sometimes it's better to use the original definition. So it all just depends on the kinds of problems you're looking at. But what I wanted to say was that there are problems, many problems actually, within graph theory that are just still a mystery to people. And we don't know answers, we being the current mathematical community or computer science or any of these areas where we look at these, we don't know answers to some very, very simple problems, even problems with trees. And so I'll give you one of these, which I learned when I was, I think like 12 years old or something, but it was really, for me, it was like a really kind of shocking that people didn't know this. They still don't know the answer. There's still no proof. There's a conjecture. People know what a conjecture is? People know what who knows what a conjecture is by a thumbs up? Who's asleep? By a thumbs up. Emma's asleep. Oh. Okay, all right. So asleep or conjecture? I shouldn't have asked two questions. All right, so hopefully people know conjecture. So conjecture is like a statement that we don't know whether it's true or false. We don't know if the statement is true or false. Often conjectures, I don't know if this is true. So I think many conjectures, more conjectures than not, most people think are true. Like they make the conjecture because they believe it to be true. But certainly some conjectures have turned out to be false. So they just don't have an argument for it. So there's a conjecture. This is called the graceful labeling conjecture. I'll share it with you guys. It's really cool. So it states, it states that you can label the vertices of a tree 1, 2, all the way up to n, so that the edges weights given by the absolute value of the difference of the vertices is 1, 2 to n minus 1. Okay, so I'll give you an example. So let's say we had this graph. Maybe I'll start with this graph. So I have to kind of remember some of these. So let's say we have this graph. So we have five vertices, 1, 2, 3, 4, 5. So let's go 5, 1. 4. Okay, this is a gracefully labeled graph. Because if I look at the difference, so if I've labeled the vertices 1 through 5, and if I look at the edges, if I look at this edge, I can make the weight, which is I take the difference of the vertices, 5 minus 1, take the absolute value, which is in this case just, so the difference of the vertices is just 4. Difference of these two vertices is 3. Difference of these 3 and 1 is 2. And the difference between 3 and 2 is 1. So I get 1, 2, 3, 4. For the width. So this is a conjecture that given any tree, you can make this labeling so that you get these differences. And it's unknown. They've computed it like for trees that are pretty big and been able to find them. But in general, they don't know if it's true or not. So there are questions. The only reason I bring this up is because there are actually really simple questions in math, throughout math, but certainly in graph theory that just haven't been solved. We're still working on them. And these have applications in sort of various fields, but I don't want to get into that. Okay, that's not in the book. I thought I'd bring it up. It was one of the this was one of the first conjectures when I saw that I was like, oh, this is really cool. All right. So now let's get back to sort of some of the material and talk about the redundancy of a network. So what we want to do is we're going to use trees along with, and notions of trees along with notions of just networks in general. And we'll talk about sort of subgraphs and things of that sort, but we want some notions that help us to give us a little more vocabulary, not much more, but a little more vocabulary to help us answer some simple questions. So let's say we have a network N, or we have a network with N vertices and M edges. These are two numbers. Then the redundancy is going to be defined the following way. We're going to take M, the number of edges, and subtract away N minus 1. This is the redundancy. So this is R. Why is it the redundancy? What does that mean? Well, what is redundant? It's like one of my daughter's favorite words. I don't know why. Because I say things over and over again. Well, let's take a look. Let's say I have a graph like this. Okay, this graph has 5 vertices. And it has, let me count how many edges. 1, 2, 3, 4, 5, 6 edges. So the redundancy here is going to be 5 minus, pardon me, 6 minus 5 minus 1, 4, which is 2. And the idea is that if I look at a path, I mean, maybe one of the ways you can think of redundancy is the following. We'll have some more details in a second on various ways we can think about it. Is that if I had a path like this, there's other paths that are sort of, redundant paths that I could use getting from, so let's say this is A and this is B. Right. And how many kind of choices can I make to kind of change this path? Well, actually, in general, this is not quite true, but here it is kind of true that I can take this edge in the path and kind of go change that to that path. So if I did that, that would give me one change, which would be like this. And then I have another change I could make where I take this part of the path and kind of switch it to that. And so if I did that, then I'll get that path. So I have two kind of switches that I can turn that will allow me to go from one path to, other paths. And that the redundancy should sort of capture that, vaguely capture that. I mean, this is not precisely the case in general, because there's sort of overlapping switches sometimes, but this is the kind of idea of why it's called the redundancy. So you have different paths giving you between two single vertices. Whereas with a tree, let me ask people this, with a tree, what is the redundancy of a tree? Have I lost you guys? Yes, I've lost you. Okay, thank you for answering the question. All right, so the redundancy, so what are we doing here? We're trying to, okay, here's what let me step back a little bit, or sit back a little bit. We have a network, and we want to define some some things about that network. So maybe give some numbers about the network that will help us understand kind of qualitatively what's going on. Now, there are a couple of things that we can do right away, right? We can count vertices, that gives us a number, and we can count edges, that gives us a different number. Now, there were other things that we were interested in, like the degree of separation. So the degree of separation is very intuitive for graphs, right? It's just saying how many, like how far apart are two nodes in the graph or in the network. If you think of it as a friendship network or a social network, how, you know, and you want to play the phone game or whatever, like how many people does this message have to go through before it gets from one person to the next, to the other person that you're interested in. Diameter is another number that we have, which is sort of the maximal degree of separation within a given network. But now I'm giving you another notion, another number that will help us qualitatively understand a given network, and that's this redundancy. The formula is not hard, right? If we know the number of edges and we know the number of vertices, we can just stick those numbers in and we'll get our redundancy, not a big deal. However, what is the qualitative meaning of it? Well, that's what I was trying to do here. I was trying to say, well, qualitative meaning tells you sort of how much freedom you have in the number of paths from one vertex to another, generally speaking. It's not completely true, but it's generally speaking. And now I'm saying, okay, let's say I had a tree. Let's say my network was a tree. What is my redundancy for a tree? What is this new number that we're defining if the network we have is a tree? So I have one guess of 1, which is, well, actually, I had this like a debate with myself. I don't really know if 1 is the loneliest number, right? I mean, you guys ever think about it? Like 0 is a pretty lonely number. Yeah. I mean, 0 is a really lonely number. It's like nothing. I don't know. Anyway, so Jenna suggests the loneliest number, the number 1. Any other suggestions? The redundancy is sort of the number of different paths. I mean, this is not, okay, there are, it's sort of, this is, the redundancy, it depends on the graph. So if the graph is connected, if the graph has bridges, where you are on the graph, all makes a difference into this description I'm giving. What I'm saying is sort of in certain cases, the redundancy can tell you how much freedom you have in choosing a path between two vertices. If you have a high redundancy, that means that there's probably a lot of paths between two given vertices. However, you can always, like, if you just go across a bridge, there's always only one path across a bridge, right? It's a bridge. So if you take it out, there's no paths between it. So like if it will depend on where you are on the graph, but the redundancy gives you sort of a global picture of, okay, this is sort of how much freedom you have generally between choosing them. So if I have a tree and I have 2 points in the tree, how much freedom do I have in selecting the path from one point to another in a tree? Let me ask that question. You guys all get zeros except for Jenna and Bailey and Joseph for participation. It's the worst. You guys are the worst. All right. That's why I like being in class. So I can berate you face to face. I'm kidding. All right. So if I'm in a tree, guys, if I'm in a tree and I take two points, right? How many paths can I get between these 2 points in a tree? 1. I agree with Bailey, 1, right? There's one path between them. So there's no freedom. There's no freedom of choice there. You have to choose the one that you have. So that means that the redundancy should be 0. Like that's kind of the intuition should tell us that the redundancy should be 0 here. But if you don't like that kind of qualitative argument, you can look back at the other property we have that we went through and talked about, which was this, the n-1 edges property. A tree always has n-1 edges, so this number m has to be n-1, and here you're going to get n-1 minus n-1, so the redundancy always has to be 0. So there's that too. All right, guys, I think I'm basically out of time. This was so much fun. I'm sad that we probably won't repeat it often, but we'll see. I'll post this up and see you, hopefully everybody, on Friday. Can I talk about that, how that diameter problem was 3 real quick? Yeah. Good. So there was a question about why the diameter of this graph is 3. Well, so I'm going to look for 2 points that are sort of farthest apart in the graph sense. Okay, and when I look for 2 points that are farthest apart in the graph sense, when I look at all of these points here, they're all distance 1 apart, right? There's an edge between all 3 of them. So these are all distance 1 apart. Same with over here. These guys are all distance 1 apart. So if I want kind of larger than a distance larger than 1, I'd have to take something over here and compare it to something over here. Maybe F and C have distance 2, or degree of separation 2. So, and if I look at D or E, well, let's see. Let's take D, for example. What's the degree of separation? To E, it's 1. To C, it's 1. To A and B, it's 2, because I have these paths, 1, 2. And then to F, it's also 2. Right. So D has the maximal degree of separation from D and any other vertex is 2. And the same thing you can say for E as well. However, once I look at F and A or B, either one, I can see that the degree of separation from F to B, for example, is 3. Because I have a path, the smallest path between them, or the shortest path between them, has length 3. So that means that the degree of separation between these is 3. Similarly, the degree of separation between A and F is also 3. And what is the diameter of a graph? It's the largest degree of separation. So you look at between all of the different points, you find their degrees of separations, and you take the largest value, and that's your diameter. So that's why it's 3. This diameter this degree of separation between A and F gives us that largest value. Does that help, Chandler?
Yeah, I'm just kind of confused. Like, why can you not, since you're already gone through C and E, why can't you go through like A, B, C, D, E, F?
Okay, so I'm not saying that you can't, that there isn't this path. That's a good question. I mean, it's a little confusing. So what is the diameter? The diameter is not the longest path.
Right.
That's not what it is. It's the largest degree of separation. So if you think about a diameter of, what do you know the diameter of in general? You know that if you have a circle, what is this diameter? Well, okay, it's the largest distance between 2 points on the circle. So it's that largest, distance. However, it doesn't say the length of the longest path between 2 points, because of course I can take, a very long path between these 2 points in space. So it's that distance that we're maximizing. And the distance that we're using, our notion of distance here, is this degree of separation. So the distance between F and A is 3 here. Even though there's a longer path, we define the distance to be the shortest path between 2, the length of the shortest path between 2 vertices. Does that help?
Yes, sir. Appreciate it.
Okay. All right, guys. I will see you Friday. Thanks for coming, and have a good snow day.